Hi guys, let's continue with aromaticity. And let's pick up here with structure and molecular orbital diagrams of anions and cations, basically charged molecules. And we will see that charged molecules can indeed also be aromatic or anti-aromatic, or actually non-aromatic. Let's start with this 5-membered ring here. Cyclopentadiene, it's called. Okay, is it aromatic, anti-aromatic, or non-aromatic? Note that this is an odd-membered ring, 5-membered ring. Previously we were looking at even, 6-membered, 4-membered, 8. Okay, this is a 5. All right, 2 pi bonds. But we have to focus in right here. This carbon is sp3. Okay? That carbon does not have a p orbital. And so it cannot be a cyclic conjugated pi system. Thus it cannot be aromatic or anti-aromatic. It is non-aromatic. All right? It's a diene. It's a conjugated diene. It's 2 alkenes. But what if we considered the carbanion? Okay. Somehow maybe a strong base took an H, left the lone pair behind. We formed a carbanion. What hybridization do we expect for this carbanion? And we expect sp2. Okay. With the LP in the p orbital. In organic 1, we said many times, anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. So, let's consider structure here. We're going to put this in a p orbital, this lone pair. Why? Because there's p orbital next door. Now we see that pi bond next door, one electron makes pi bond. One electron makes pi bond. That's the pi bond we see next door, yeah? Of course, we have overlap here. All right. But by putting this lone pair in a p orbital, and now having a p orbital on this carbon, we now have overlap here as well, and on both sides. So we have continuous pi overlap all the way around. That is 5 p orbitals with 1, 2, 3, 4, 6 pi electrons. Okay. Now if we did an MO diagram of the molecular orbital energy levels, 5 p orbitals would give us 5 MOs. Okay, I'm going to do an abbreviated look at this. We'd have one low one, then we'd have 2, and then we would have 2. Here are 5 MOs. In terms of energy level, we're not showing the actual MOs. The midline would cut symmetrically through here. Now how do you cut through with an odd number? Well, you got to keep in mind, when we cut through symmetrically, it's not really the number of orbitals that's going to be symmetrical on each side, it's the energy. All right. We can also use the Frost mnemonic. And if we draw the structure with the point at the bottom, we get the 1, 2, 2. And the midline, if you drew this actually correct, the midline you would see does not split through the two carbons here, but just above it. In any event, this is how it splits. These are going to be bonding molecular orbitals. These are going to be anti-bonding. Okay. 0 nodes, 1 node, 2 node. And we have 6 pi electrons, and when we put them in, we get 4, 5, 6, all electrons paired. And this is the main thing. Any event, if we just focus on a cyclic conjugated system with 6 pi electrons, Huckel's rule tells us that a cyclic conjugated pi system with 6 pi electrons will be aromatic. Okay, Huckel knew that if we drew a diagram, they would all be paired. Okay. 6 is a 4n plus 2 number, where n is 1. Cyclic conjugated system with 6 pi electrons. It is aromatic. It's an aromatic anion. Now, on the other hand, if we look at the 7-membered ring, okay, this was a 5, 7, we can do the same, have same considerations. Boom, 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 boom. Let's see, 1, 2, 3, 4, 5. We've got to come across here. Boom. I really didn't put the point at the bottom. The point is not at the bottom here anyway. Let's see here. We have, I see 3 pi bonds. Let me kind of turn it a little bit. It's kind of as shown there. And this carbon here is the anion. But if we put that in the lone pair in a p orbital, why? Because there's p orbital next door. Because next door we see pi bond. 1 electron makes pi bond. 1 electron makes pi bond there. So there's the 3 pi bonds. Of course, there's overlap here and here as well. And now we have here and here as well. And so we see by making a p orbital on that carbon, we have a cyclic conjugated system with 1, 2, 3, 4, 5, 6, 7, 8. 8 pi electrons. Okay. Cyclic conjugated with 8 pi electrons. And Huckel's rule tells us that a cyclic conjugated pi system with 4, 8, 12, or 16, that is a 4n multiple, 8 is a 4n number, should be anti-aromatic. Okay? And not aromatic. Now, the problem though is this molecule does not want to be anti-aromatic. And we can go back and say, well, making this sp2 and putting the lone pair in a p orbital is not a stabilizing thing. That's not a stabilizing structural consideration. It doesn't lead to stability in this case. In this case, it leads to an unusual instability. So we might ask, why would this carbon want to be sp2 then? Maybe it would prefer to remain sp3. Okay? And indeed, that's probably what it does. It's only anti-aromatic if planar. Okay? instead, one, two, three, four, five, six, 7, 8. Instead, what probably, I'm not going to draw the pi p orbitals, I'll draw just the pi bonds. Instead, this lone pair is probably going to exist in a hybrid. Okay, there is an H there. All right, like that. And the preferred hybridization here is likely sp3. And if that's the case, it's not anti-aromatic, but non-aromatic. It's no longer a cyclic conjugated system. See, in organic 1, we always said anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital, because that's a stabilizing effect. It's more stable for the lone pair to be conjugated with the neighboring p orbitals. But that is usually the case. In this case, conjugation of a lone pair led to it being anti-aromatic. Because, by the way, if you did a molecular orbital diagram of this, you would see that it would be a diradical. You can do that. There are actually very few anti-aromatic compounds, because if the compound can sort of adjust somehow, if it can avoid being anti-aromatic, it actually will. All right? So I would more likely label this as non-aromatic because of this right here, yeah? Now, importantly, it's certainly not aromatic, because if you consider the cyclic conjugated system, we see it has 8 pi electrons, and if you did a quick MO diagram, quick and dirty, it'd be 1, 2, 2, 5, 7, and 8. The midline would come through right here, right? And we would have 1, 2, 3, 4, 5, 6, 7, 8. There you go. You would see you have a diradical. Again, Huckel knew. Huckel saw this trend here, this consistent trend, and that's why he was able to come up with his rules. But I doubt it's a cyclically conjugated system, and so this doesn't really apply. It's non-aromatic. All right, certainly not aromatic. Let's look at cations. Can cations be aromatic like this one was? Okay. Well, first off, this molecule here is same as above. It's non-aromatic because it has an sp3 carbon with no p orbital. But what about the carbocation? Now the carbocation I think that's right. Is that a 7? Okay. Carbocation is going to be sp2. All right, sp2 with empty p orbital, just as we would expect. I mean, if you have a carbocation like this, it'd be trigonal planar because there's 3 regions, okay? And that would be sp2 We'd have this and a p orbital. Let's see, bond to carbon, and sigma bond to carbon. All right. And the p orbital would be empty. And so I'm showing empty p orbital there. But then we also have the pi bond next door, one electron mixed pi bond. One electron mixed pi bond. One electron mixed pi bond. Of course, these are also overlapping, and these are also overlapping. And if this is a p orbital, we can overlap p orbitals here and here. And we have a cyclic conjugated system with how many pi electrons here? 2, 4, 6. There's none here. 6 pi electrons. Cyclic conjugated system with 6 pi electrons. That equals aromatic. So while the 7-membered ring carbanion here was non-aromatic or anti if planar, the 7-membered ring carbocation is aromatic. By the way, we can draw resonance structures of these and give a resonance structure argument. All right, these electrons can go here, these electrons can come out. Pi bond there, electrons here, minus. These electrons here, these electrons out. Minus. These electrons here, these electrons out. Minus, and these electrons here and these electrons out. And we see that by resonance we can actually delocalize the negative charge onto every carbon in the ring. And if you blend these together, what does the hybrid look like? It's actually going to be well, we can show it sort of like this. And if we back that up, that comes from, well, each bond is really a bond and a half. And you see, and we can just show the entire thing being charged, and a lot of times that's just shown like that. Same thing down here, we could draw resonance structures and we could end up with a hybrid that really looks like this. We can actually place this positive charge on every atom in the ring by drawing resonance structures. And these are fully delocalized ions. All right. So this was a cyclic conjugated system with 6 pi electrons. Now here, if we considered this, I reckon I'll do it over here. Let's consider this empty. And then we got pi bond here. And pi bond there. Of course, these overlap as well. These could overlap if that's a p orbital there. Cyclic conjugated system with 4 pi electrons. And Huckel's rule tells us that that would be anti-aromatic. Okay. Again, if planar. Now this is likely indeed planar because that's most likely sp2 with an empty p orbital. I can't see it with any other hybridization. So I would consider this guy here, this cation, carbocation, to be anti-aromatic, while the 5-membered ring carbanion was aromatic. All right. So ions can also be aromatic or anti-aromatic. Now, consequences of that. For example, on acidity. If you look at these two hydrocarbons here, they look pretty similar in terms of structure. We could envision a carbanion here if these acted as acids. But there's a huge difference. This one has a pK of about 16. This one has a pKa of greater than 40. Because when these act as acids, this molecule here, the conjugate base would be let's call this A. All right. And then let's call this B. The conjugate base of B would be here. And so which of these, upon acting as an acid, or which is more likely to act as an acid? Well, the answer is A, because when it acts as an acid, it becomes an aromatic carbanion. When B acts as an acid, it becomes this conjugate base, which is either anti-aromatic, and that'd be very bad. Why would B want to act as an acid and become an anti-aromatic carbanion? It would not want to act as an acid. Now, possibly that carbanion is just non-aromatic. But if it's non-aromatic, it does not have the stability that an aromatic carbanion would have. And in fact, if there's no aromaticity here, this carbanion has very little stability because carbon just doesn't like being minus. So, in the end, this one's much more acidic because it becomes an aromatic anion upon acting as an acid. And pK of about 16 is pretty darn high. Well, it's actually low. It's pretty darn strong, I should say. Okay, it's pretty darn low for a hydrocarbon. Most hydrocarbons have pKa's, 35 to 40 range. Now, another application or consequence of aromaticity can be seen here. If you take this alcohol and try to do a substitution reaction with HBr, Okay, and these reactions look like they should be SN1 with carbocation intermediate. All right, protonate the OH, water leaves to make a carbocation. This would be a 7-membered ring carbocation, and that would be, if it happened here, that'd be the 5-membered. Both of those carbocations were shown over here. All right, here's the 7, here's the 5. Which carbocation is more stable? Well, the 7 is. It's aromatic. The 5 is anti-aromatic. So which intermediate is going to be more easily formed? And forming that intermediate, the carbocation, is typically the rate determining step for such reactions. All right. Well, the 7-membered ring carbocation, that's why this reaction is very easy and fast. But this reaction is very difficult and thus slow. May not even happen. All right. Trying to form an anti-aromatic carbocation, going to be very difficult. Okay, let's look at aromaticity of heterocyclic compounds. And we'll begin with heterocycles with a pyridine type nitrogen. Here's pyridine itself, nitrogen with a lone pair. And pyridine is basic. We need to understand the hybridization, the bonding structure here. What type of orbital is this lone pair in? All right. Lone pair is sp2. If you graph that we would expect sp2 for that nitrogen. There'd be a p orbital left over. I see a sigma bond to carbon, a sigma bond to carbon, and a pi bond to carbon. And then the lone pair has to be in an sp2. So the lone pair is not conjugated. And that's why the lone pair has some basicity. If you can see here, the nitrogen being sp2, trigonal planar. That's the trigonal planar there, and then the p orbital is perpendicular to that plane. We have pi bond there, and pi bond between carbon and nitrogen. Each p orbital has 1 electron. You see a cyclic conjugated system with 6 pi electrons. The lone pair is in a hybrid orbital perpendicular to the pi system. So that's a pyridine type nitrogen. You see that type of nitrogen in a variety of heterocycles. And so it's commonly seen, so I call it a pyridine type nitrogen. On the other hand, we can have pyrrole type nitrogens. Now this 5-membered ring is called pyrrole. The drug Lipitor, as shown on a previous handout, contains a pyrrole ring with substituents on each carbon and nitrogen. Okay, we can replace this H on nitrogen with something else, as well as the H's on carbons with a substituent. Now in this case, the lone pair is in a p orbital, because anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. This is that exception. Early on in Organic 1, you may have thought this should have been sp3 because it has 4 regions, but it's actually sp2. And if we graph it as sp2, energy, of course, we see a sigma bond to carbon, and sigma bond to H. Then the lone pair is in our p orbital. All right, this is turned sideways. We have pi bond there. The circle that was shown up there is not shown here. Pi bond here, of course, those are overlapping as well. But the nitrogen, we have a p orbital, and we're going to put 2 electrons in it. And so with the p orbital there, it can overlap. I can draw top and bottom. Yeah. It gets a little messy when I start doing that. But we have a cyclic conjugated system with 1, 2, 3, 4, 5, 6. And a cyclic conjugated system with 6 pi electrons is going to be aromatic. Of course, pyridine was aromatic. Pyrrole is also aromatic. Both have 6 pi electrons. Big difference though with pyridine, or with pyrrole, the lone pair is conjugated and it contributes to those 6 pi electrons. But in pyridine, the lone pair is not conjugated, and the 6 pi electrons come from your 3 pi bonds that you see. Now, because the pyrrole lone pair is conjugated, that lone pair is not going to be basic. Typically not going to be wanting to react with a proton or with any other type of electrophile. And as we said in Organic 1, a lone pair that's conjugated is typically not that basic, not that reactive. So this is a pyrrole type nitrogen. Now, some example heterocycles that contain these types of nitrogens. The imidazole ring contains both of these type nitrogens. It has a pyrrole type nitrogen and a pyridine type nitrogen. It's called imidazole. Only one of those nitrogens is basic. You should know which one it is. Now, the imidazole ring is found in the amino acid histidine. Here I have the sides of the ring drawn straight, parallel to each other. Sometimes you can draw the 5-membered ring with the sides not straight but sort of slanted, and that's how this is drawn. And then here, of course, the NH is drawn condensed. There the NH bond was drawn out. An amino acid is considered a basic amino acid because one of the nitrogens in the side chain is basic. Here's a drug that contains these types of nitrogens. It's actually 3 here. It actually is an imidazole ring here if you look. 5-membered ring with 2 nitrogens separated by 1 carbon. Aromatic. We also have this nitrogen here. Now this larger here, 1, 2, 3, 4, 5, this larger 7-membered ring doesn't really have a common name. But we can still look at this nitrogen and consider the hybridization and the basicity of that nitrogen. And if you do that, you'll see that this nitrogen looks like a pyridine type nitrogen. Now, what about atoms other than nitrogen? If you take pyrrole and replace the nitrogen, and of course one other group, NH or whatever the nitrogen's bonded to, if you replace the nitrogen with oxygen, you have a compound called furan. Now oxygen only makes 2 bonds, so there would be no other bond here. And furan is aromatic, and the oxygen is sp2, with one of the lone pairs being conjugated. Okay, and if we graph that, we would have sigma bond to carbon, sigma bond to carbon. Then we'd have two lone pairs, one in a p orbital and one in a hybrid. So furan is going to look just like pyrrole, one in a p orbital, and in this hybrid, instead of making a bond to something, a lone pair just sits there. Now, same thing for thiophene. Oxygen and sulfur have the same bonding, so anything we said for oxygen should apply to thiophene. It's also aromatic. All right, same hybridization setup. These are cyclic conjugated systems with 6 pi electrons. And then I also show borole here. Okay, what do we expect for borole? I'll let you think about that one on your own. I have to consider the boron, of course. Do that on your own. All right. Now these are some very common heterocycles. Pyridine, 6-membered ring. These 5-membered ring heterocycles, pyrrole, furan, and thiophene, super common. They're all aromatic. Okay. They each are cyclic conjugated systems with 6 pi electrons. Okay, so we looked at some aromatic ions, some consequences of aromaticity, acid-base, reaction rates that may involve, reactions that may involve a aromatic or potentially anti-aromatic intermediate. And then a look at some heterocyclic compounds that are aromatic. But we left this one open here for you to think about. Borole. Okay, guys, we need to look back at some of this here between the videos. We'll try to do that in class. Aromatic, anti-aromatic, or non-aromatic. All right. We'll end this video here.